want to welcome you to another exciting topic in statistics. Of course, uh, I think this is going to be like second week of our lecture, and today we got a lot to discuss. I'm also going to be showing a video today, if everything works out. So you're actually going to see, because I'm going to use, I take a reference from a celebrated case in Los Angeles, United States, some years back, how Bayes' theorem was actually used in the court of law to decide a case. Okay, so, but I'm going to first start with this. We started further topics in probability. And of course, initially, I posted 3 lecture materials for the week. I changed my mind. And of course, we're only going to have 2 lecture materials. You can see that Monday and Wednesday, we committed that to the first lecture of the week. And of course, this is going to be the last lecture of the week. And of course, today, we actually going to discuss further on topics in probability. Particularly, we're going to focus, number one, on system reliability. You're actually going to see how probability is actually being used in system reliability. Then from there, I'm going to walk you through Bayes' rule in odd form, how the conventional formula of Bayes' theorem can also be written in another form that we call Bayes' rule in odd form. And of course, lastly, we're going to see how, if you take a look at that, can statistics help guide a verdict in the court room? Okay, I'm also going to show maybe a 2-minute video. Of course, you're going to see how a celebrated case was actually decided using the idea of Bayes' theorem. What I just need from you is to sit back. If there's any area you need clarification, please let me know. I'm going to start with system reliability. We find ourselves in a world where there's variations, right? Our things are changing. And not only in human beings, also in components, in system, in system reliability, we actually want to know, okay, how reliable is our system. Of course, we've seen some systems that fail. We don't want a situation where there's going to be a sudden failure. Can we have a way to tell about the reliability of a particular system? The knowledge of probability can actually be used to figure it out. I got this belief, if we want to leave this world successfully, of course, we need to be probabilistic inclined. Okay, and that is why the knowledge of probability can actually be used to be able to evaluate how reliable is our system. So when I'm talking about system reliability, of course, we got different types of system reliability. Okay, of course, when I talk about reliability of a system, we actually expect a system to perform the task that it was designed to perform. And the moment that system is not actually doing that, of course, we know there's a problem. Okay, we don't want problem to happen, but we want to have a way to make a kind of prediction ahead. Okay, now we got 3 types of system reliability. We have series system, parallel system, and series, the combination of the two. Okay, but I'm first going to walk you through before I move into probabilistic implication of that. When I talk about series system, okay, the belief is, in a system, of course, you got components, right? Components that are connected. I want to believe those of you who offer physics, before must have heard about how resistors are connected in series, how resistors are connected in parallel, and of course, they actually investigate the amount of current that pass through that for those of you in physics. But you know what? What we're talking about is not peculiar or to physics only. We're talking about system reliability in general. So when I talk about series system, okay, of course, in a system you have some components, and in a series system, for system to work, for this system to function, all the component has to work. The moment one particular component fails, the system is going to fail for series system. I want you to understand that. I can give you an example when you take a look at a motorcycle. Okay, a motorcycle without, if just an engine is faulty, of course, the motorcycle can't move. What about gas? Just one component. The moment one component fails, the whole system is going to fail. Okay, then I'm also want to talk about the parallel system now. In a parallel system, okay, if one component fails, the system is still going to be working, but the system is not going to work if all component fails. Okay, just give me 1 second. Just give me 1 second. How are you doing? Yeah, yeah. Actually,
Yeah, I'll try to do it.
have this video to show. Yeah. So no, no, no. So if I want to go back there, like, what am I gonna?
Okay, so basically treating this like a second monitor.
Okay.
So when I go to like this page, you go,
Okay. Okay. I'm just gonna.
like see your cursors here, right?
Oh. Okay.
And then you go to the right.
Oh.
The
I
cursors
got it now. Thank you so much. Thank you. I really appreciate that. Okay. Sorry about that. Okay. On the parallel system, of course, the system is only going to fail if every component fail. Okay, and I'm going to give an example. An aircraft. Okay, the aircraft has two engines. Okay, if one engine fails, okay, the aircraft is still going to be functioning. Although it is advisable for the aircraft when if one engine fail, the aircraft supposed to seek an emergency landing. Okay, but what we're trying to talk about is just the reason why the aircraft is still functioning. If one engine fail, is because the two engines are independent. Of course, in probability, I've walked through what I call independent, right? Okay, now, and in a series parallel system, of course, we're actually going to have the combination of the two. Now, what I'm going to do now, I'm going to walk you through how probability can actually be applied here. Let's take a look at this example. I'm going to start with a series connection. Okay, a simple computer consists of a processor, a bus, and a memory. Of course, a computer, right? That's a system, right? That's a lot of components. Okay, so the computer will work only if all three are functioning correctly. Okay, the probability, they say if all the three are functioning correctly, of course, we are talking about a series connection here. Okay, now the probability that the processor is functioning is 0.99, that the bus is functioning is 0.95, and that the memory is functioning is 0.99. When you take a look at the three components here, none of them has a probability of 1. Can you see that? None of them. If any component, anything, any unit, human being, or whatever does not have a probability of 1 functioning, then that is not 100% reliable. That is the meaning. Okay, so you got a probability for each component. Now let's see the graphical representation of that. Take a look at that. Now, when you have something in series, Of course, you can see the input, the processor has 0.99, or the bus has 0.95, and the memory has 0.99. Now we want to look at the output. Output in terms of reliability. Okay, now if you want to apply probability rule to series connection, okay, you're actually going to use the product rule. We're going to multiply the probability of all the components. Because you know why? If you take a look at the processor is on its own, bus is on its own, memory is on its own. So take a look at, so you're just going to multiply. So if I want to know the reliability of the whole system now, all what I just need to do is, to multiply the probability of each component. And in the end, the probability of the whole system now is 0.89. When you take a look at the 0.89 here, this is less than 90%. And don't forget, each component has a reliability more than 90%. But when you take a look at the whole system as a whole, it's not up to 90%. So take a look at its interpretation. Okay, so the overall reliability of the computer is less than 90%. Of course, we got 0.893475. Okay, there's another example. Okay, there's another example. If you have 5 components, in this situation now, there's possibility. Each of the components may have the same probability. Okay, they may have the same probability. Here is 0.97 or 2. Okay, so the general formula now, if I have n components, okay, if I have n components, I'm just going to, and if I have n components and each of them have the same probability, what I'm just going to do, that number raised to power n. Right now, I got 5 components. They are connected in series, but they got the same probability value. Okay, that's what I'm going to do. Now, what do you see? If I try to increase from 5 component to 6 component to 7 component, and with the same probability, you're actually going to see that the probability, the overall reliability is going to be going down. The more the components. So that is the takeaway. Any question? Any question? Okay, I'm going to go to the next one. Now, I want to go into another example now, but this time around parallel connection. Okay, an electric product contains 100 integrated circuit. The probability that any of the circuit is defective is 0.001. Now, I wanted to see a defective to be a complement of working good. Do you understand? Of not defective. Because defective and not defective, they complement each other. Okay. So right now, if the probability of it being defective is 0.001, the probability of not defective is going to be 1 minus that. Does that make sense? Please take notes. Okay. And the integrated circuit are independent. Please watch out for those keywords. Independent. You've been told. The product operates only if all the integrated circuits are operational. Of course, anytime you hear that, your mind should go to parallel series. Parallel connection. For the parallel connection, the only way the system is actually going to fail, that. I already told you. What is the probability that the product is operational? Okay, now I'm going to show you the system now, the connection now. Okay, this is a parallel connection. The series connection is going to be like horizontal stuff, right? The parallel connection is going to go like that. So anytime you see something like that, that's a parallel connection. Because at times, I'm just going to draw a diagram, just going to give you a diagram, and you're going to be the one to figure it out. You need to identify whether it's a parallel or series connection. Okay, now how do I find the probability? How do I find reliability when it comes to parallel connection? Okay, what I'm going to do is I'm going to use a different formula. Okay, in the case of a series, I multiply, right? I multiply all the probability of the component, but this time around, I'm just going to do 1 minus, okay, the 1 minus, okay, another 1 minus. Take a look at that. Take a look at this. Because the reliability in a parallel connection It's talking about the probability at least one component is functioning. At least, I told you, if the only reason why the whole system is going to fail if all the components fail. That's what I mean. But the system is still going to be working, okay? It's still going to be working if at least one component is functioning. Okay, so which means I want to find the probability of at least one component is functioning. Okay, and if I want to do that, we have mathematical way to do that. At least one is in statistics. Take a look at this. At least one means this greater or equal to one. Oh, at least one. What is the complement of this guy? The complement of this guy is just going to be this guy, right? The complement, right? This is one or more. Okay, this is less than one. Okay, now if I want to write this in terms of complement, I can write this equal one minus that. You remember where I'm actually talking about the probability of A is equal to 1 minus the probability of the complement. Okay, now what is x less than 1? Okay, 1 minus x less than 1. Okay, if x is a discrete random variable, if x less than 1 is just going to be 0, right? It's just going to be 0, right? So if you take a look at it, 1 minus the all component fail. I'm talking about when s equal to 0. S less than 1. A component fail, right? That's what I'm talking about. Now, if I'm now going to apply the rule 1 minus, okay, then what I'm going to have here is going to be 1 minus what you have here. You have 0.97 here, right? What is 1 minus that? Okay, why do I raise it to power 5? Because I got 5 out, I got 5 components. But what if in a situation where it is not the same? Here I got 0.97, 0.97. What if, let's say for instance, I got 0.97, 0.93, 0.94. Okay, what am I going to do? Here it's going to be 1 minus 0.97, 1 minus 0.93, 1 minus 0.94. Any question? This is a situation where you have different values. Okay? But if you have the same values like this, just the same value, you're only going to write it just once, then you raise it to the number of components. Any question? Any question? Okay. Now, for 2 components, that's what I'm going to have. But for 2 components, if I'm still using 0.97, okay, for 2 components, for 3 components, for 4 components, there is something I want you to see here. In the case of series, okay, in the case of series, when the number of components increases, the probability of reliability decreases, right? For the case of series. But for the case of parallel, what happens now? For the case of parallel, when the component increases, what happens to the reliability? It goes up. Yeah, go ahead. You said what?
I was going to say it's more.
Okay. Yeah. So what I'm going to say, like, look at the behavior for series. Look at the behavior for, for the, what is it called? For parallel. Okay. I put several examples here. This time around, some may have like component 1 and component 2, 0.95, 0.95. Component 3, 4, 5, take a look at that. Now consider that, and you have this. If you take a look at what I have here, this is looking like a series parallel. But you know what? There's so many ways to do, to approach this. You can, of course, resolve the parallel to series. To like, for instance, if I want to start, I can, of course, work on this guy, right? When I work on this guy, I'm going to get a new value, right? I'm also going to work on this guy. I'm going to get a new value. You know what I'm going to do at the end of the day? All of them now, I'm going to treat them as a series. Does that make sense? I for us to work on the parallel one, resolving the parallel one, getting a value for that. Then I'm so that is what I did there. Take a look at that. You see that? Any question? on how I figure it out. Like here, a 4 of us find the probability of at least like here, and do the same here. Okay, so whatever I got here is what I put here. Whatever I got there is what I put here. Then I'm now gonna consider them in series. Considering them in series is multiplying the probability of each component. Go ahead. When I resolve this guy, when you resolve a parallel, it becomes a single value connected in series to the other one. When you resolve this guy here, okay, when you solve this, when you want to solve this one now, you will get a single value at the end of the day, right? Using the parallel on it. Now that single value is connected to other ones in series. Does that make sense? So that's what I mean. Okay, so that's an example of series parallel connection. That's another one. Very easy, right? That's another one. Oh, that's another one. That's another one. Okay, that's another one. Okay, I think I explained all of that. Okay, that is about reliability. Okay, let me tell you this. This is very, very useful in system engineering, even in medical field. Okay, so that is how probability can actually be used. Okay, I want to go to the next objective of the day. I've discussed with you Bayes' theorem.